Okay. All right, so we just talked about isomers, and what we're going to talk about now is some 3 common isomers that we see. And so we're only going to do isomers of 3 carbons and 4 carbons, right? Once we have 3 carbons, then the groups that we add to a parent chain for an alkane can start to get complicated, right? Because the same way, so if this is our parent chain, right? So this molecule would be what? Pentane, right? It would be pentane would be the name of this molecule. And let's say we start with a 3 carbon group on here. That means in the center carbon, I'm going to put 1, 2, 3, right? So this technically changes the length of the total chain. I'm going to make it hexane just so that we don't run into that issue. I'm going to make it heptane so that we don't run into that issue. And so this group right here has 3 carbons, right? How can I make an isomer of this group? Yep, if I take this carbon and I just slide it down there, right? So this will 2 like this. So I took this group and just slid it to the second carbon. Now I still have a 3 carbon group, but it's an isomer. And so when we're naming these groups, right, if it's a group and not part of the parent chain, how do we adjust the name of the group? Do you guys remember? The suffix when it was the parent chain was ane, right, because it's only single bonds. What was it when it became a group, right? So if we have a methane group, if it's just we have a methane molecule, right? If we add that as a group to a main chain, it goes from methane to, does anyone remember? Methyl, right? So you replace the suffix with YL. An ethane group, which is 2 carbons, becomes ethyl, right? And once we get to 3 carbons, now we have to distinguish between isomers of that group, right? So 3 carbons, what was the prefix for that? Does anyone remember? Prop, right? So this right here is just a normal propyl group. And so the way we would name this would be on the 1, 2, 3, 4, 5, 6, 7. On the 4th carbon, right, we have a propyl group, right? So that group is called, it's on the 4th carbon, so we put a 4 to indicate what group it's on. Propyl. And then the name of the chain for this molecule is going to be what? Heptane, right? Because it's 7 carbons, so it's hept, and then ane because of single bonds, right? So this is only single bonds. Hept because there's 7 carbons in parent chain. And then this is our group, our carbon chain, the only carbon atoms, our side group, which is called an alkyl chain, right? So this is a 3 carbon alkyl chain on the 4th carbon, right? So 3 carbon alkyl chain because there's 3 carbons in this chain right here. Right, so that's just a review of how we name this alkane. And so when we change the group to a different isomer of that group, this is now going to be numbered the same way still. 3, 4, 5, 6, 7. This is now called 4. And then the isomer of the propyl group, this one is called isopropyl. Right, so that kind of makes sense. It's an isomer of propyl. It's the only isomer of propyl, right? So it's just called isopropyl. Isopropyl, and then it'll also be heptane. 4 isopropyl heptane.
Sorry, how do we know it's isopropyl?
That's just because it's still a 3 carbon group, right? 1, 2, 3. Here it's 1, 2, 3, but the connectivity is different, right? So it's an isomer of propyl. So that's why it's isopropyl. And then it's not, there's no rhyme or reason necessarily to a lot of these names. That's just what it was named.
Alright, so if that was like on a quiz, we'd have to have both of them to know if it's an isomer?
No, you'd only be given like this molecule, and you would just have to say that this is isopropyl.
Okay, so you have to remember.
Yeah, so isopropyl is a peace sign, if you want to. That's how you want to remember, right? Isopropyl is a peace sign.
Okay.
But this is an example of how, you know, we've changed, right? These are both still have the exact same chemical formula. They just have different connectors. This is technically an isomer of this molecule, but really what's changed here is it's an isomer of the propyl group, right? And that's why we have to indicate that in the name of the molecule. The name is supposed to be like a map from the name to the structure, right? If we see the name, we should be able to draw the molecule. And if it's a different isomer of that side group, we need to be able to indicate that in the name somehow.
So then, like, when you just have like the chain coming down from the 4,
Mm-hmm.
that's how you know when it's like that chain structure. Then
When it's
just
you-
the propyl hexane?
So yeah, so like I don't really like to kind of trick you guys. Sometimes I have a better molecule drawing software now for organic molecules. But a common way that you'll see in like standardized tests that people will trick you is that if this chain is longer than what goes vertical here, the main chain still has to be numbered according to the longest parent chain, right? So you would, if this one you actually get the same if you number it. Actually, no, you don't. Yeah, you do. 1, 2, 3, 4, 5, 6, 7, right? So you can number it that way, or you can number it 1, 2, 3, 4, 5, 6, 7, like how we did. But if you did it, you'd get the same name either way, right? Because that's still a propyl group that comes up from there. This one, right? 1, 2, 3, 4, 5, 6. That's not as long a chain as 1, 2, 3, 4, 5, 6, 7. So we have to keep, this is the correct way to number that chain.
And Isomer will be in that case, we can change on the carbon number 5 to have both coming out like
Say that one more time.
harmless. Like if we want to if we go with the longer chain
Mhm.
down way, then on the 5th carbon we will have the propyl.
It would, well, so that wouldn't be, if we were to number it this way, it would give you the exact same molecule, right? So if I numbered it 1, 2, 3, 4, 5, 6, 7, like that. Now, we see that on the 4th carbon, which is still the same carbon, there's a propyl group coming out of there. So it would still be 4 propyl heptane, because it's still a 7 carbon chain.
But what would be the iso for that one?
Oh, well, yeah, then I would just move this here. I mean, it would look exactly the same. The molecule would be exactly the same. So if I moved, you know, so if it was 1, 2, 3, 4, I'm going to make this 1, 2, 3, 4, and then 1, 2, 3. Right? I could move this last group here over, and then I could make that molecule, and then it would give you the same thing if I made the isomer there. Really, if I was to draw this better, it would be the exact same. It would draw these bonds, because they're single bonds, can rotate around each other. They can rotate, and these molecules are very flexible, right? So these molecules are very flexible. So this molecule and that molecule are exactly the same. They're not isomers of each other. They're exactly the same molecule. All that's changed is that we've named it, or we've, you know, numbered it a different way and then named it, but it's the same molecule, right? So I think last time I was talking a little bit about how a lot of these times you can name the molecule. That's technically not the most correct way, but you still arrive at the same structure, right? Like technically we always want the group to be on the lowest possible number. The highest priority group goes on the lowest possible number. So there's rules to name it, and then the groups go in alphabetical order when you name it. But if you didn't put it in alphabetical order, you would still get the same structure as long as you put the right numbers there, for example. Or if you numbered it wrong, but it was still consistent, like you just numbered it backwards, then it would still give you the same structure, right? So right now we're not worried about getting everything perfect. You would still get, you know, vast majority of points just for getting this name to the structure, right? That map from the name to the structure is what's important right now. But there is a priority system for how that works. Right, so when we change the isomer of the side group, that changes the name of the side group. And so what are the different groups? So there's going to be 3 carbons. We're going to have propyl and isopropyl. Right, those are our side groups. And usually if there's a bigger part of the alkane chain and you don't feel like drawing it, or a bigger part of the molecule that you don't, I'm not drawing this every time, I'm just drawing the same molecule over again, how you'll see that represented is just by an R. And then the propyl group comes up like that, right? So R here equals the parent chain. I don't feel like drawing.
Like the carbon chain.
Yep, it's just some other carbon chain at that part. Right, because I don't, propyl is independent of the carbon chain. That can be on, pentane, heptane, octane, octene. It can be on any cyclohexane. It can be on all of those. We're just trying to illustrate what the different groups look like right now. And so then isopropyl is the peace sign. And we're only going to go up to 4 carbons. Once you get to 5, then the isomers start to get pretty complicated. So we're not worried about that. So 4 carbons. What's the parent, or what's the prefix for 4? Bute, right? So prop. This is going to be bute. And if it's only single bonds, it's butane. If it's a group, it becomes butyl. So these are butyl groups. If we have our R group, and then 1, 2, 3, 4, this is called N butyl. Right, so you're like, well, this looks like the normal butyl group. Why is it called N-butyl? Well, because N stands for normal, so that's the normal butyl group. Then we have 1, 2, like this. This will be isobutyl. This is called secbutyl. Make this a little bit more apparent. And then the last one is called tertbutyl. And that one looks like a chicken foot. Tert with a T. Right, and so really what you're seeing is you're just moving these different methyl groups around, right? The first one, we just slid this one down here to create the peace sign at the end of the chain. Then to get from isobutyl to secbutyl, this methyl group slid down here, right? So that was the peace sign right there. We put a methyl group right there. And then to get the last one, we slid that last methyl group. So they're all attached to the first carbon there. And this is one of those things that if you forgot on an exam, you could ask me and I would give you the name of these different isomers. But you would need to phrase the question like, what's the different isomers for butane as a side group? And then I'd be like, oh, okay, I'll give you the isomers.
Is there TERT, right?
Yep, TERT, and then there's a dash right there. And the important thing when these are side groups, when you're naming, is that since technically we're supposed to be going in alphabetical order, the isomer doesn't count towards alphabetical order, right? So they're butyl groups, which means that B is where they go in alphabetical order. Butyl is always going to go before ethyl, for example. It doesn't matter if you have tert-butyl, you still are only looking at the B in terms of alphabetical order. I told you, these next, what is it? What are we at? We're 6 weeks away from being done?
I know exam I'm dropping.
No, you guys will do fine on it. We're 6 weeks away, right? It's going to be a lot of information that's kind of like coming at you. It's basically the whole second half of the book. All right, so these are the isomers of small carbon chains. And so, like I said, this, to be able to look at it and recognize their isomers is important. Memorizing what the different isomers are, not as important. On your note card, this would be something you can put on your note card that could be easy to reference. You know, this is something that you just pick up from doing a lot, right? Like the more practice you get it, the more you'll kind of do it. So it's not that important that you just memorize everything right now. Okay. All right, any questions on this? All right, so then we're gonna get into our first organic chemistry reaction, the only one we have for alkanes. And so this is called the halogenation of alkanes. It's a substitution reaction, right? So substitution. Let's see, where's my pen? Substitution. That means that we're replacing atoms on the molecule, right? So if, for example, in this reaction, we have hydrogens on a methane, we're going to be replacing those hydrogens with some halogen, right? Which halogen is our group 7 elements, fluorine, chlorine, bromine, or iodine. So if we have methane, so let's say it's methane gas, CH4, right? That's what our methane molecules look like. We have one carbon atom, so methane because there's only single bonds. And then we, let's say, bubble hydrogen gas over it. And what that's going to do is it's going to replace hydrogens with chlorine. And so then this is going to be called chloromethane. All right, so this is methane, which we can name now because we know how to name organic molecules. And this is chlorine, right, because it's a diatomic in its natural form. So we just call it chlorine. And then depending on how long you run it, on how long the reaction proceeds, that determines how many H's are replaced. Right, so for a halogenation reaction, the longer we let the reaction proceed, the more hydrogens that will be replaced on the methane molecule. So if you run it long enough, eventually you'll have tetrachloromethane, right? You'll replace every single hydrogen with a methane.
Sorry, that's CH3C.
CH3Cl.
This
And
with any halogen?
this works with any of the halogens. I mean, actinium, no, because it's radioactive, but all the other halogens, yeah. So I had a lab last week where the students, they had to use iodine to catalyze a specific reaction. They used an iodine crystal. Sorry, I forget this is so low. And I had one student that didn't listen to how long he was supposed to boil it for. So I walked over to his fume hood and there's purple gas bubbling up because he's basically halogenating all the organic compounds in his reaction flask. Alexis? Lunchbox in there.
Where's that word?
Hmm?
Proceeds.
Reaction proceeds determines how many hydrogens are replaced, right? So the longer you let this run, the more you'll halogenate the molecule. So for example, fluorinated carbon chains or polymers, a lot of times you just bubble a halogen over it, and then you make, carbon fluorine bonds, which is what makes a lot of like non-stick stuff and whatnot, because that forms very, very stable structures. Okay, so this is our first reaction.
Non-stick is, it's just repelling.
Yeah, because it's so inert. So that's the issue with a lot of microplastics, is they're so inert, which is why they're like, oh, they're safe for everything, whatnot. But actually, once they get into the body, all these microplastics and stuff, they're so inert that they don't do anything. Like they just stay around. And then so now why people are saying, oh, there's an issue with microplastics is because, well, they're so inert that the only way they break apart is just through physical force. So they just, turn into smaller and smaller plastics. And then when they're that small, interesting physics happens and they kind of just accumulate. So they're still not reacting with stuff, but they accumulate. And that's what people don't really know how that affects the body, really. So that's why there's this a lot of talk about microplastics right now in breaking down a lot of like fluorinated carbon chains and stuff like that, or most very, very stable polymer chains. But like, huh?
Is it partly because like chlorine in the water, is that, or like?
It's
or the fluor-
well, it's fluorine is the really, really stable one. So those are used because the carbon fluorine bond is so strong. It's one of the strongest bonds you can have. And so it's really hard to break that bond. And so because it's such a strong bond, that's why you use it on pans a lot of the time, like Teflon, stuff like that, is fluorinated carbon chain. Because it basically, even if you heat up the nonstick pan, right, it's not going to cause any reactions to happen. It's still going to stay, your Teflon is still going to stay on your pan. The only way that you really break down this nonstick of the pan is, does anyone know? Does anyone use no? Huh? Yeah, if you roommates that piss you off that use your fork with your nice nonstick pans and then they scratch the surface of it and then you lose the nonstick pan. So that's the only way that you can really break down those molecules. It's like physical force in abrasion. So when they get in the body, they don't react with anything, but because they're so stable, if they get broken down into very, very small pieces, they kind of just sit in your body. Like, so there's no blood sample on Earth right now that doesn't have microplastics in it because they're so stable. They don't think they're doing anything weird in your body yet, but you start to wonder, okay, if these start to accumulate this much a lot over time, how is that going to affect things? Like, that's taking up physical space. And also, in general, when things become very, very small, they start to react, or they start to have interesting physical properties, for example. So, like, quantum dots a lot of times are metals that, they conduct electricity. Metals are very inert and everything. And when they're, have a big piece of metal or like, your pen metal, it doesn't really react with a lot of stuff. But once you get down to very small objects, that metal can then serve as like a catalytic surface for a lot of reactions and stuff because small things behave interesting. So
Do you,
So-
in dialysis, would microplastics be removed?
So usually they can be, it depends, right? So it's hard for them to move across a membrane. There's a lot of research being done right now into, I'm not familiar with all of it, for how to purify microplastics from things. Because they're so inert, generally what drives things at super small sizes is intermolecular forces, right? But if you're so inert, so stable, it's hard to filter you out from, in general, other nonpolar things, right? So you don't want to filter, everyone's, red blood cells through, like, how would you separate the nonpolar lipid membrane or something from a microplastic? And that would be very hard to do because they have similar chemical properties. So, and because they're microplastics, they're so small that you can't use just physical filtration because they'll go through the pores in the membrane filter. And it's not so small that you can't do something like a ion gradient that allows single ions to go through because there's no chemical charge on the microplastics too. There's a pretty, you probably win a lot of money if you figured out how to filter out microplastics right now. A lot of what I think main method that people are searching for filtering them right now isn't through physical filtration, but through degradation somehow, right? So one of the things people are trying to do to reduce greenhouse gases isn't to filter, greenhouse gases from the exhaust right away, but maybe as you're going, you're making methane or something like that, you can convert it into methanol, and methanol is not a greenhouse gas. It'll just evaporate and it's fine. So the causing a chemical reaction would be ideal, but it's hard to do that with such inert plastics. So that's kind of like as far as I know, that's like the main way people are trying to filter water microplastics from groundwater and stuff like that, is through trying to degrade them through chemical reactions instead of just physical filtration. But yeah, so you guys are all bright students with a bright future. You guys should spend some time thinking about that. Maybe win a Nobel Prize if you get bored with this class. So.
Give you a shout out.
Yeah, I remember when I first heard about this. Then you link the YouTube video, and they're like, actually, what he said was wrong. I'm like, oh, damn. Okay. All right, so then now we have halogenated alkanes, right? So how do we name a halogenated alkane? Well, we use a number to indicate where on the chain the halogen is. this indicates where on parent chain the halogen is, right? And the same way with when we're naming alkyl groups on a chain, you want to put the halogen at the lowest possible number. And so this, should be the lowest possible number. And we're not too worried about it right now, but there is a priority to things. So if you have, for example, an alcohol group on one side of the chain and a halogen on the other side, the alcohol group takes priority, so you number it to put the highest priority group as the lowest possible number. But if we only have halogens on there, you're just making sure that that's the lowest possible number. And then if there's multiple halogens, you need to add a prefix. If multiple halogens, we need a prefix. And I'm probably going to give you of a single halogen ever if I was really, wanted to add a lot of the same halogen to a molecule would be 4. So it would be like, we don't put any prefix for 1, so no prefix for 1. And then for 2, it'll be di. For 3, it'll be what? Tri. And then 4, what's 4 going to be? Tetra. 4 will be tetra. Right, so that's multiple on the same chain. Right, so remember last time you guys had two methyl groups on the same chain. You had to use a number and a comma to separate the two numbers to indicate where the different groups were. And then you used a prefix to indicate how many of that group there were on the lab. So it was like if you had a methyl group on 1 and another methyl group on 2, it was 1,2 dimethyl, right? So it's the same idea with halogens, except you're replacing the name with the halogen group name, which is just replacing the halogen with the suffix O. So for example, fluorine becomes fluoro, chlorine becomes chloro, bromine becomes bromo, and then iodine becomes iodo, right? So it becomes iodo. And then you just add a prefix depending on how many there are, right? So if we have, let's go through do I have any? Okay, yeah, so I have some spots on the next one. All right, so it's similar to rule, and then, as we kind of go along, you'll see that really, as we add more functional groups and different types of groups, the same kind of basic rules are there for each of the different functional groups. So understanding kind of the naming of the alkanes is a good foundation for understanding everything else. It does get really complicated when you start to mix in double bonds, different functional groups, and there's all, you're like, okay, this seems just like a mess. You'll always be able to write a name that tells you what it is, but you just don't know if it's the most correct name for that structure. But we're going to try and keep things simple enough so that when we're testing carboxylic acids, I'm not going to be, combining that with every other functional group you've learned at that point. Okay, so let's name the following 2 compounds. So we have a chlorine there, and then let's say here we have 6, and then we have 2 fluorines on this molecule. To number this, it would be 1, 2, 3, 4. The groups go before the name of the parent chain, and the numbers are separated from the letters by a dash, right? So what goes first then? Yep, it's going to be a 2. So that'll be 2, and then what's the chloro, right? Chloro, right? Because this line doesn't represent a carbon atom at the end of that line. It represents the bond from this carbon atom to this halogen, right? So whenever you see an atom that's not carbon in the carbon skeleton, the line that goes to that atom isn't an extra carbon atom at the end of this line. This is the bond from this carbon atom to the halogen itself. Right, so there's no CH3 right there. It's CH2 bonded, or CH bonded to Cl. Right, because technically there's 1 hydrogen there, because how many bonds are shown right here? 3, right? And we need how many for carbon? 4, so that means there's an extra hydrogen right there.
So CH3, Cl?
Yeah, so this would be CH3, CHCl, CH2, CH3 is what the not so condensed formula would look like. So we have 2 chloro, And then what's the name of the parent chain? Bute, because there's 4. And then what's the suffix for that? Ane, because there's only single bonds here. Butane, right? So this would be 2-chlorobutane. All right, so spend a second then using that, apply that to the second molecule. All right, so we need to put the groups on the lowest possible number, right? So how are we going to number this chain? From left to right or right to left? Right to left, right? Because if we put 1, 2, 3, 4, 5, 6 versus 1, 2, 3, 4, 5, 6. Here in the blue, we would have the fluorines on the 4th carbon, and in red we have it on the 3rd carbon, which means it's on the lower number in red, right? So that's how we number the chain. And then we have to indicate where our group is. What is our group here? Our groups are? It's the halogens, right? And they're on which carbons? 3. And then do we just write 3? We have to do 3, 3, right? Because, let me do this in a different color, right? So these are our groups right here in blue. So we have 3, 3, right? Because we need to indicate that where each fluorine is. They're both on the same carbon, so we just have to write that same carbon twice. So 3, 3, and then what do we write? Dash, because whenever we separate numbers and letters, there's always a dash there. So it's dash, difluoro, right? Because we need the prefix for fluoro because there's 2 fluorine atoms on the molecule total. So it'll be difluoro. And then what's the name of the parent chain? Hexane, right? Because there's 6 carbons, so that's why that's hex. And then ane because there's only single bonds. So 3, 3, difluorohexane. All right, how do you guys feel about that? Thumbs up, thumbs aside.
The
Mm-hmm.
fluoro, the O is what indicates that it's an isopropyl.
Huh?
Is the O indicates that it's an isopropyl?
The O is because when we name halogens, we replace the suffix of the halogen with O.
Okay.
So it's fluorine, right? And then fluoro. So again, these right here, these lines here, they don't represent carbon atoms. They represent the bond from this carbon atom to the fluorine. And this one from this carbon atom to the fluorine. Right? So there's no isopropyl in this chain, right? There's only 1, 2, 3, 4, 5, 6 carbon atoms. These 2 lines right here are the bonds from the 3rd carbon to the fluorine atom. Right? So there's no carbon atom that's right here. Right? There's no carbon atom that's right here. This is how we would draw this full structure, is if it was 1, 2, 3, 4, 5, 6, like that. How many bonds does each carbon have? 4, right? So we just make sure each carbon has 4 bonds. And then on the 3rd carbon, so I'm going to put 3 right here because that's where the 3rd carbon is. There's going to be 2 fluorines bonded to that, right? And then everywhere else is filled with hydrogens. Right, so those 2 structures are exactly the same. This is just the full formula, and you see that there's no C to CH3 or C to C to F here. It's just a straight bond from carbon to fluorine.
Like on the quiz, you would give us like name the halogen, right? You tell us halogen, and we have to know.
So either on a quiz or something, I would just give you this molecule and I'd say name it. Right, you'd have to recognize that there is a halogen there on the molecule, and then that's how you're gonna have to name it.
Okay.
Yeah, so it's.
The other one would be carbon, you know, right?
Say that again?
Like
Yeah, so for example, let's do, am I good to go on to the next slide?
Yes.
Yep. So let's do one that mixes both of what we've learned so far. So let's say we have 1, 2, 3, 4, 5, and then here we'll do BR there. Okay, so how did you guys number this chain? Right to left, right? Because the terp butyl group will be on the same our carbon atom either way. So to put the bromine on the lowest number atom, we go from right to left. 1, 2, 3, 4, 5.
So do we prioritize the halogen or the carbon?
Technically, a halogen will have a slightly higher priority than that. I'm not going to be testing you guys on distinguishing between the alkyl groups and halogens. If you, like I said, I'm not going to be super strict about getting everything in alphabetical order the first time. Technically, you number it this way. Probably the most correct name to actually name this molecule is if you numbered it 1, 2, 3, 4, 5 like this, because then you have dimethyl, ethyl, and bromine. And that's the most substituted chain, and that gives you the longest name. But that would be kind of cruel to do that for this example. So we're gonna name it according to this numbering convention right here. All right, so then what goes first? Yep, because we have the bromo group right here. And then on the third carbon, we have the terp butyl group. So it'll be 2 dash, and then what? Bromo. Right, we put 2 dash bromo because this 2 belongs to this bromo. That's telling us where the bromo group is on the chain. And then we separate the numbers and the letters by the dash. And then what do we write? Yep, then we need another dash because we're letters and numbers separated by a dash. Another dash, and then what's the name of the group? Tert butyl, right? And tert butyl has a dash in its name, so that's why that dash is there. Tert butyl, and then how long is the parent chain? 5, so it should be pent. And then the suffix is ane, right? So that's 2 bromo, 3 tert butyl pentane. And the reason we don't put the numbers together is because if you don't have the numbers together, you don't know which group is associated with what number. So I think the confusion, Israel, might have been if you put 2, 3, and then bromo tert butyl pentane, right? But you don't want to do it this way because then you don't know if 2 goes with bromo or 3 goes with tert butyl. Yeah, that's just the name though. That's just how it's named. And N-butyl is the same thing. If you forget the dash, that's not a big deal to me. So the name just has a dash in there. Right? The important rules, letters and numbers separated by a dash. If there's multiple numbers next to each other, they're separated by a comma. Right, so that uses 2 different groups we've talked about. We have an alkyl group, which is a single bonded carbon group, and a halogen, or halogenated alkane here. Okay, all right, so let's look at this example. So why don't you, this is the other way that we would go for these types of problems. We can have the name and draw the structure, or I can give you the name and you draw the structure. If we have the structure, we name the molecule, or I give you the name and you have to draw the structure. All right, so remember, these are just supposed to be a map between the structure and the name. The name a little bit. So we start off, the first thing I always do is identify the parent chain, right? And how many carbons are in the parent chain. It's easy to have the parent chain and just put groups on it, right? So that was known, right? So that tells us what? 9 carbons. Ane tells us what? Only single bonds. So I'm going to draw 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And then, now I'm going to dissect the rest of the name. 2, 3 tells me what? A group on 2 and 3rd carbons. So now I'm going to number the chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's easy to draw the structure from the name because you can number it however you want, right? You're not going to be tricked into having to number it backwards, left or right, or anything like that, right? So that tells me there's going to be a group on 2 and 3. Di tells me what? 2 of the same group. And then bromo tells me what? The group is a bromine halogen, right? And then there's 2 of them. So I need to make sure that each one is on. Oops, sorry, not there. It's 2 and 3, so there's going to be 1 on carbon 2 and 1 on carbon 3. All right, did everyone get that structure?
For,
What is that?
the dye, no?
Hmm?
We only had 2 on 3, it's dye.
But there's 2 total on the molecule. That's why we have the prefix di. The numbers tell us what 2 carbon atoms those are on, right? If they were both on 3, how would the name change? It would be 3,3 dibromo, right? So remember here, we had 2 on fluorine, so it was 3,3 difluoro. Yeah, and we need to indicate that both of them are on the number 3. Here we have 2 bromine, 1 on 2 and 1 on 3, but we have 2 bromines total, right? So the prefixes are for the total number of that group on the molecule. So if we had something 1, 2, 3, 4, 5, 6, 7, 8, 9, something like this, and I put a methyl group on 4 of them, that becomes 1, 2, 3, 4. So 2, 4, 6, 8. 2, 4, 6, 8 tetramethyl, whatever the name of the parent chain is, right?
And that prefix is only if they're the same kind, right?
Yeah, that means however many of that group is on the chain, right? So it's like we have 5 methyl groups here, and they're all on different atoms all over the molecule, but I'm just consolidating all of that structure into one part of the name, right? So I want to keep the numbers associated with methyl next to each other, right? And the prefix tells me how many methyls are total on the molecule.
Okay, so instead of, if it was like 1 Br and like 1 F, it would be just 2,
Mm-hmm.
3 bromo.
It would be, if there was 2 different ones, we'd have 2 fluoro, 2 dash fluoro, right? So let's say, do I have another one? Okay, yeah, I have another one right here. So let's say that it was 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say that it was fluoro, and then bromo here, right? Both of those have the same priority, so we're just gonna number it 2, 3. It would be 2 dash bromo, and then what goes after that? 3 fluoro, and then we don't have to put a dash after that because it would just be nonane. Right, the dash only separates the numbers and the letters. Everything else is like one giant run-on sentence, except in a name.
If you switch the bromine and the fluorine, would the name be?
Technically, yes. I'm not gonna have you guys do that, but technically, if it was bromine before fluorine, bromine has a higher alphabetical priority order, so you name it the opposite way. But like I said, if you did 2 bromo, 3 fluoro, I guess in that case it would be 3 bromo, 2 fluoro, you would get the same structure as if you wrote, 7 bromo, 8 fluoro, kind of thing. You get the same structure if you did that. So I wouldn't take any points off for that. Right. And then if you had, oops, I accidentally put an L here, but there is no L. If you had 2 fluorines there, how does that change the name? You need difluoro, right? And you need to indicate 3,3. Fluoro nonane. Right, you need to indicate now that there's 2 fluorines there on the molecule, so there's di, and they're both on the 3rd carbon here. any questions on that? Thumbs up, side, down, side. Okay, so we'll get plenty of practice doing this. Okay, so the next thing is cyclic structures for alkanes. And so these form closed loop carbon parent chains. So the parent chain here forms a closed loop. Write that here. Right, so the parent chain forms a closed loop, and that basically makes these ring structures. And so for naming for these, we just add a prefix, cyclo. So if we have an example, what's the name of that molecule? Butane, right? If we make it a closed loop, what shape should that make? Square, right? Because there's 4 of them, 4 corners. This molecule now becomes cyclobutane. Am I good to go on to an example? Let's see. We don't need to draw the structural formula, condensed structural formula. All right, I'll make one. So if we have this molecule, right? So now we have a cyclic molecule, we need to know how to number the chain. We're always gonna put the number 1 at the highest priority group on the chain, right? Since there's no edge to it, we don't go from left to right or right to left. We just start numbering it from the highest priority group here. So I said halogens have a slightly higher priority group, so where should the number 1 go for numbering the chain? On the fluorine, right? So it'd be 1, 2, 3, 4, 5, 6. You could number it counterclockwise too, and you'd get the exact same numbering scheme for this. In general, you want the numbers to be as low as possible, the same way for a normal alkane. All right, so spend a second and just see if you can come up with the name for this molecule. You raised your hands a couple times, and then every time I look back, I continue talking, your hand has gone down. Do you have any questions? On the previous slide, I saw you had a question.
Yeah, but it's okay. I think I have.
You got it? Are you sure? All right. Okay, so this is, sure. So we're starting with 1. That's how we're going to name it. We're going to put the highest priority group on number 1. So how are we going to name this molecule? I'm going to highlight the different groups here. All right, these are our 2 different groups. How do we name this? What goes first? We have 1. You don't have to put 1, but I'll do it just because it makes it more obvious. But in general, for a lot of cyclic molecules, you don't have to put 1 here, because if you have fluoro 4-cyclohexane, the fact that 1 isn't there implies that fluorine is at 1, just because it's a higher priority group. I would put 1, and I'm not going to mark you down for putting 1, but technically you don't have to put 1, right? Chemists don't like writing the number 1 for some reason. So we have 1, and what goes there? Fluoro. Then what's after that? Dash. And what's the 4 what? 4 dash. What goes on 4 though? methyl, right? Because it's a 1 carbon atom group, right? This is a single carbon and it has 3 hydrogens. This is a methyl group, right? So this becomes 4 methyl, and then what goes after it? Cyclohexane. Then you put the cyclohexane after, right? So all we did was instead of hexane, we just add cyclo to it, cyclohexane, right? Ane tells us what? Only single bonds. Hex tells us what? 6 carbons in parent chain. And then cyclo tells us what? Parent chain is a cyclic molecule. Chain is cyclic molecule. 4-methyl tells us what?
Carbons on and
Methyl on 4th carbon. And then 1-fluoro tells us fluorine on 1st carbon. Right, so the name, each part of the name tells us something about the structure. We're going from the structure to the name, name to the structure. The formula? Like if I was to just... Oh, so this would be, yep, it would be C7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, CH13, F. Mm-hmm. It would be fluoro-4-methyl cyclohexane. Yep. So if you don't have to write one because that implies that the highest priority functional group on a ring structure is always going to be the number 1. Right. So we're not going to ever get into aromatic compounds like benzene and stuff, but benzene, for example, there's specific names for each functional group on the benzene atom. Right. So for a benzene structure, what I mean by that, the parent name of each chain, if it's NO2 versus OCH3 or something like that, right? These are benzene rings. Those have specific names. One's called nitrobenzene and the other one is called anisole, right? So those have a common name mixed in with this IUPAC naming convention that we're using, but you never indicate the number for those on that ring. Why? Because the name tells you what's on the first carbon. Right, so that's way beyond the scope of what we're going to go into in naming. So here you don't have to put it because fluorine has the highest priority. So if you just put fluoro in a cyclic structure, that means that's going to be the number 1 carbon. If we get into other groups, like what we'll get into eventually, is we'll have an alcohol group there. Alcohol has the highest priority of everything. So then you're going to have to put alcohol or OH at the number 1 carbon. And then you don't have to put 1 cyclohexanol, right? Because it turns into an alcohol. We are not talking about that yet, but you just say cyclohexanol and that implies the alcohol is at number 1. Is what I'm getting at this point. That's probably a week or 2 away. Okay. All right. So I have a bunch of a couple other names here that we'll kind of skip over for now. Draw the structural formula for cyclohexane. This is trying to go between carbon skeleton, condensed formula, and whatnot. You guys can go over that on your own. It's, we've done a lot of going between the different structures. Just be good practice. The only thing I want to talk about before we take a break, and then if you guys want, you can stay and work on the lab. Actually, let me end this lecture.